should be fine now. So, hi everyone to our talk on NoSEBrEaK and defeating Honeynets. Sorry for the small delay. We had some problems with the internal network and with the two beamers. So, who of you knows what a honeynet is? Just as a question. So many people know. So I can leave the. I just give a short overview over honeynets. A honeynet is, according to the definition by the Honeynet project, a concept in order to learn the tool tactics, and motives of the Black Hat community. A typical honeynet is depicted over on the slides. As you see, a honeypot typically consists of two applications. The one is the honey wall. The honey wall is a transparent bridge and has two things to do. On the one hand, data capture. On the other hand, data control. Data control means that you install Snort Inline there. Snort Inline is an intrusion prevention system. It's based on Snort. It basically just turns the rules so that someone who owns one of your honeypots can't use an exploit to the outside world. So the exploit is blocked at the honey wall. On the other hand, we do some kind of traffic shaping. For example, that only a limited rate can be the outgoing network flow, or only perhaps 20 TCP connections per day are allowed. The other main function of the honey wall is data capture. That means that you've got a TCP dump or Snort running so that you capture all network traffic that's flowing inside and outside of your honeypot. You also can do data logging of the honeypots on the honey wall. The main part of the honeynet is, or are the honeypots. A honeypot is a resource whose value lies in being probed, attacked, or compromised. That means you're interested in who scans your box, who attacks your box, and what do they do if they own your box. So typically you use a Linux, Solaris, a Windows, or some kind of BSD as an operating system. You just modify it in some small ways, and then you just deploy it. So you've got a couple of servers who have no production value. They just run, and you watch them if they get scanned, if they get attacked, or perhaps someone even hacks them. So you want to learn the tool tactics and motives of the Black Hat community. How do you do that? Of course, you have to observe them. But how do you observe someone who's doing things on your net? On the one hand, you've got the TCP dump, so you control all network flows. But the network flow is not interesting if it's encrypted. So if the attacker uses SSH or some other kind of encryption, you can't basically see nothing because you can't decrypt the traffic. So you have to find other ways in order to see what an attacker is doing. If you use some kind of Trojan binary, for example, a Trojan SSH, for which you've got the keys, it's useless if the attacker deploys its own tools. For example, his own tool that decrypts the session. So you have got to do another approach. The approach that's currently taken by the Honeynet project is NoSEBrEaK, a tool that has a capability to monitor all activities on the honeypot. For example, you can log all SSH connections. See if someone copies a file via secure copy to your honeypot, you see what's going on. If someone, for example, a burn-eye protected binary has to be decrypted before you run it, so you also get the password for the burn-eye protected binary. So it basically allows you to see many of the things that can be done on a honeypot. NoSEBrEaK also provides the ability to monitor all internal workings of the honeypot. So if no one is connected to your honeypot, you also see what's happening. So if someone owns your box, installs some toolkits, and then logs out, you also see what's happening on that box. And how does NoSEBrEaK archive this? Basically, NoSEBrEaK is a rootkit. In the first version, it was based on Adore. Adore is probably known for you. It's one of the best rootkits currently on the earth, perhaps. In the current version, version 2.1.7, it's based on, or it's completely rewritten. And the main part of NoSEBrEaK is the hijacking of this read. So you hijack a syscall, you override it with your own one, and if someone calls now read, you pass this value to the original syscall, and the result, you add a header and send it in a covered way via UDP to another host where all things can be logged. How do we send this in a covered way? It basically creates an SK buffer structure, fills everything in, adds its own header for the NoSEBrEaK, and then passes this SK buffer structure to the driver, and the driver just sends it on the net. You have to fiddle a bit with the network counter so that no one can see that you're doing some kind of observing. And you've got also some, in the header, some kind of magic value so that you can identify if some protocol or if some packet is a NoSEBrEaK packet. So if NoSEBrEaK is installed on every computer on your Honeynet, you basically can't see on any of these that NoSEBrEaK is working, because NoSEBrEaK also hides on the upflowing network layer that you can see this. So all your libpcap-based sniffers and all firewall rules are useless against NoSEBrEaK. We don't want to see that, an attacker shouldn't see that NoSEBrEaK is running on the host. So we have to hide it. So basically, as a rootkit does this. How do we hide NoSEBrEaK? In the default installation, NoSEBrEaK is just a kernel module with a random numeric name, but you can also customize it. For example, we use snd-pcmca.o as a name for our NoSEBrEaK presentation later. Afterwards, a second module, cleaner.o, from the Adore rootkit is loaded. Cleaner.o is a very simple kernel module. It basically just unlinks your module from the module list and then unloads itself. With no pointer in the module list, it's hidden in some kind of form, so you can't see NoSEBrEaK very easy. To give you an impression about NoSEBrEaK, we just demonstrated how it works. We've got here a Mac with the IP address 10.11.12.1 and a Linux box 10.11.12.1. Currently, here's no NoSEBrEaK running, but we'll install NoSEBrEaK now on this host, and then we'll extract all these packages that are sent in a covered channel to the Mac, and then you'll see that I can't see anything here, but he can see anything what's going on my box. So basically, NoSEBrEaK is a kernel module, so you have to have root rights to install it. Max is currently installing it. Now NoSEBrEaK should be running. If I type something on this box, perhaps an ls on ID.
It's not running.
It's not running?
No.
Okay. So I have to wait a bit. As we can see on the size is not as big as we expected, so we will have probably some little problems to show you everything, but I hope we can manage it so that you see on the first window, this is just my computer. Now NoSEBrEaK is installed. As you see on the first part, snd-pcmca is loaded. This is just NoSEBrEaK in another name. After this, cleaner.o from Adore is loaded, and it unlinks NoSEBrEaK from the module list, and now we can see basically everything. NoSEBrEaK is running. On the other window that now should pop up, there's some kind of logging running. So we've got, if I type something in here, perhaps an ls, an ID, and uname minus a, shit. So you should see on the other side what commands that I type in, something like this. And so basically, NoSEBrEaK is able to see everything what's going on your box. So back to.
So who we are and why we are looking into NoSEBrEaK. We are a research group at the University of Aachen, and we are running a Honeynet ourselves. And following good scientific practice, we see the Honeynet as a research tool or as a probe into the internet, and we have to attack our measurement devices and probes to assess the quality of data gathered by this tool.
Sorry.
Our main concern is what quality of data does NoSEBrEAK or us provide under the view of attackers circumventing NoSEBrEAK. Can we really rely on that we see all attacks on our machines, at least hinted at in the log files provided by NoSEBrEaK? The authors of NoSEBrEaK were hoping that even if people are able to disable NoSEBrEaK, they would see how NoSEBrEaK could be disabled. We were not sure about that and tried to attack the assumption, and we were successful with that. So first, as a teaser, we show you our success on that and give only very short explanations on what you are seeing and what's happening there. This is a honeypot, and this shell runs on the honeypot. And I'll now start there an HTTPS server which has a gapping security hole, so it's easy for me to exploit it. Now there's this HTTPS server running on port A443, and you see there was a lot of logging going on. This is running on my notebook, which emulates the honey wall, but today also the machine of the attacker. Now I will present an exploit code exploiting the vulnerable server, and then we will upload our own attack tool KBS, and you will see in the lower window that there will be next to no logging information. Basically now there's our attack payload is created on the fly. Then we use curl to do a connect to the insecure server and transfer the script payload sh, which is executed by the vulnerable server. And now we were too fast or the network too slow. Our attack tool doesn't work. Connection refused. That basically means that the attack tool on the server side isn't started. But now it is. So now we are able to execute arbitrary commands on the server without much logging taking place. In the lower corner you see the log window peering up under the other window, and I will now show the root directory of the honeypot without information being logged by NoSEBrEaK. I can get system information from the honeypot, like environment variables or the user ID without information being logged by NoSEBrEaK. I can read files, this is etc passwd, without being logged by NoSEBrEaK. I can upload files, and I can execute other files. In this case I will execute a vulnerable SUID program we placed on the honeypot and use it to start another server of this KBS tool running now as root. You now see there was a little logging because our server is completely coded in Python to do rapid exploit prototyping. And the Python binary, when loaded, does some things which could be logged by NoSEBrEaK. If anybody means he needs it, he can convert the tool to C and avoid this logging easily. Now I connect to the other KBS server running as root. I again can get system information. For example, you now see that the effective user ID in the middle of the screen is 0 instead of 65534, which means nobody. So now we have root. I can again show files without being logging, in this case etc shadow. And now I'm executing a special module on our server which tries to find the NoSEBrEaK binary in memory. You see again that took some logging place, but because we accessed the memory very aggressive, most of the packets were dropped, so NoSEBrEaK isn't logging anything really, but just spewing out error messages. This is because we are doing big reads in def kmem. We could have accessed def kmem by mapping it, and that wouldn't have led to logging. We should do that at some point. Now our tool detected a kernel address where we can remove the NoSEBrEaK module. And now we can jump to this kernel address, then get a funny GNU people warning that we will taint the kernel with our attack tool, which is exactly what we're planning to do. And now NoSEBrEaK is disabled.
So basically I can type now something on this box, and as you can see, no logging is running. If I type uname -a, so you don't see any output. So we basically unloaded NoSEBrEaK.
So let's have a look at how we did that and what we did.
So as you saw, we were able to detect NoSEBrEaK, we were able to avoid logging, we were even able to unload NoSEBrEaK. So basically, we compromised the honeypot.
Question?
If I could just real quick. Well, Nate, what's the point of rooting a honeypot if it can't log? What can you do with it? You're trying to get advantage anyway.
For example, you can use it as a stepping stone in the network. You can use it to attack the honey wall, which would be probably a nice stepping stone. And in fact, often I ask, what's the point in these things people are doing? What's the point of trading 50 terabytes of French movies? People just do. And basically, we are interested in, could we do? Because if we could, others could. Basically, it's our assessment on the data quality of the honeypot.
So, and now we want stepwise to explain what we've done and how we've done it. On the first part, I want to explain how we are able to detect NoSEBrEaK. If you think of it, NoSEBrEaK is basically a rootkit, so there come several ways in mind how to detect it. The first one is based on the honey wall. As I said before, the data capture and data control is done on the honey wall. So the operator of Honeynet uses not inline and some kind of connection restriction there. So you can probably just, if you open many connections or if you send an exploit from a honeypot to the outside world, if you watch it, you can probably see that there's something malicious going on in the middle. We don't go into details, that's left as an exercise. And also there was a frag article, I think, in one of the fake frags. The other thing that comes to mind is the latency. NoSEBrEaK packs everything into a UDP packet and sends this over the network and then logs it there. So if we are able to generate lots of logging data, perhaps we're able to see some latency effects so that we can make the logging unreliable and also detect that NoSEBrEaK is running. As I said, NoSEBrEaK also fiddles with the network traffic counters. Perhaps we can fiddle with them too and detect that they are changed. NoSEBrEaK also uses a simple form of syscall table modification, and also we can check the syscall if everything is correct, and then detect if NoSEBrEaK is running. With the help of cleaner.o, NoSEBrEaK loads itself and hides itself. So perhaps we're even able to discover that there's a hidden module, and perhaps we also can do some other corrupted memory in order to detect it. So in the first part, we want to go into detail for the latency. We found something that's called DD attack. So with the help of DD, a very simple tool, I can generate lots of traffic, and with the help of DD, I can generate so much traffic that the latency effects come to that you can see the latency effects and therefore detect that NoSEBrEaK is running. We've also got a small demo on this. So at first, we are already logged into the box. We then ping from there to the Mac. Let's see what the round trip time from this crossover cable is. So after that, we're going to to load another module that fiddles with the network counters. So at first we ping, we send some package, some ICMP packets. We've got a latency time of about 0.3 milliseconds or so. Then we load a kernel module that fiddles with procnetdev. So we change the counters as they were originally and see what happens.
I think we'll make that later.
Oh, sorry for me. We now start DD in the background so that we generate lots of traffic. Let's see. And now we do the ping again. As you can see, there's some very long delay now. We've got about 10 times the delay from before. So you can see that the delay is going up, and perhaps this is based on the presence of NoSEBrEaK. As you can see, it doesn't react correctly because there's so much traffic going on. It's a kind of denial of service attack against the honey wall. So, back to the demonstration. Sorry for the network traffic counters. So, as we see, as I said before, NoSEBrEaK fiddles with the network counters. It basically chains procnetdev and subtracts all SBK buffers that it sent in a covered manner. So if we fiddle everything back and then compare the output of ifconfig with the output of procnetdev, then we see that there's something malicious going on because sometimes the network counters are running backwards, or you also have jumps inside the network counters. We've got also a demonstration on this. So at first we take a look at, you see that we've got about 22 kilobyte of data. We are logged into the host via SSH, so we generate about 2 kilobyte or so per second. So now we load a module. The module just turns the counters in procnetdev back, it fiddles with the counters in procnetdev, and then everything should be, then we should see that the network counters are much higher than we expect them to be. So if we now run ifconfig, we see that the network counter is more than 30 megabytes. And if we unload the module again, so if we do an rmod on this, we see that the network counter is switching back again. As we see, we've got some delay because DD is running in the background. So now we've got more than 50 megabytes of data. So this is the real network counter, including all data sent via NoSEBrEaK over the line. And now it's back again to about 48 kilobytes. So if you just change procnetdev again to its original state, we see that that NoSEBrEaK does something with this. Okay, now to the syscall modification. There you can see on the left side a normal syscall table. This is exit, this is read, this is write, this is open. So, these are also all pointers into the kernel memory, and yes, they are all function pointers. Now if I load another module, for example NoSEBrEaK or another rootkit, it basically changes the pointer so that it points to another location. After that, every time the syscall is called, then it handles this, perhaps transfers or changes the output and gives everything back. So if we load it on a box, and normally, so this is the output of a kernel module that just outputs the memory location of the read and the write. As you see, they are not far apart. But if we now load a kernel module, then we see this read is far apart from this write. So this is also a sign that NoSEBrEaK is loaded.
So NoSEBrEaK is a hidden kernel module, and if we could find it, we could start poking into its inner data structures, to extract the variables used by NoSEBrEaK, and we probably could disable NoSEBrEaK. Modules in Linux start with a module header, which is defined in include Linux module age, and which looks like this. And it gives us a lot of data to fingerprint on and use for heuristics. First, there is the size of the module structure, which is 96 on Linux 2.4. Then we have pointers into the kernel memory, pointing to the next module in the list of modules, which should be another valid module structure, and to the name of the module, which should be an ASCII string. Then there are pointers into the module itself for the init function of the module and for the cleanup function. Then there are variables which have only a small range of values, usually between 0 and 2. And we can use all this to see if this could be a valid module structure we have found in memory. It's further facilitated this that all module header data, and in fact all module data, in the kernel is reserved by the vmalloc function. And the vmalloc function aligns memory to page boundaries, so we have only to check every 4K if this could be a module structure. And the vmalloc function starts allocating memory at vmalloc start and goes only for vmalloc reserved bytes. That is usually 128 megs. So we have to check every 4th kilobyte of memory in 120 megs if this could be a valid module structure, which is not that much. Now a presentation of that. We'll use the tool rootkit hunter, which was published in FRAC. So you see with lsmod, there we see nothing about the NoSEBrEaK module. No. Oh, I lost the tool. No. I lost the object file. Huh? So you just have to believe the screenshot. This module hunter module, when installed, it adds a proc entry show modules. If you get that proc entry, you get no output. But then if you look into D message, you have an output very similar to the output by lsmod. And you see that there's an additional module, sound PCMCIA, which is the hidden NoSEBrEaK module. And if you find out that between lsmod and the output of module hunter, there's a difference and an additional module, you can be sure that there's something very fishy. So it's a honeypot, or it's a machine owned by somebody else already, which is a kind of honeypot too. If we found the module structure, we can start to extract the variables used by NoSEBrEaK from the memory after the module structure. This is quite difficult because the authors of NoSEBrEaK started to hide the variables very good. Basically, this is a Perl program which is executed on every compilation of NoSEBrEaK, permutating the position of the different variables which are placed in a big block of empty memory. So they have this block of memory reserved in the NoSEBrEaK kernel module, and then drop at random locations the real variables, like this. And if you have a memory dump, then it looks like something like this. So there are variables scattered around the place, and the places change with every compilation. But we can start doing educated guesses if we have this block of memory, which the stuff might be we are seeing there. For example, if we have this value, this might be an IP address. But if we check, this is an IP address in the multicast range, which would be highly unlikely. We are looking in this case for the IP address of the honey wall, which NoSEBrEaK has to know to send out the data there. So if it's not an IP address, it might be the magic value used by NoSEBrEaK. Or if we look at this value, that's a valid IP address. So it might be the address of the honey wall collecting the data from NoSEBrEaK. If we look at this value, it's a nice port number. This might be used as a port for getting out the data to the honey wall. And if we look at this very short byte values, they terribly look like fragments of a MAC address. So we can use this as a heuristics to find or to guess at the values NoSEBrEaK saved in memory. This is an output of NoSEBrEaker Pi, which was on the Black Hat CD also. It's a Python program which traverses the memory structures of the Linux kernel, which is a little bit tricky nowadays because the Linux people recently decided to remove the kernel symbol for the system call table because nobody wants it and nobody needs it. Perhaps it's even a security measure. So we first have to resolve other symbols in the system call table and start scanning from there, not other kernel symbols, and start scanning from there which could be the system call table. This usually works out. So in line 6 or 7, we have found something which looks like the system calls table. And there we already see that this read is at a completely different location than this write and this open. So probably this read is hijacked, or the output of the program is wrong. It says probably this write is hijacked, which is makes no sense. So we have then we find out by via the way of the heuristics if there's a hidden module. And if there's a hidden module, we try to analyze the data structure in this module. So we have this sound PCMCIA module, which is hidden. And then we have a list of possible MAC fragments. And really, in fact, this FFFFFF is the MAC address we use for sending out NoSEBrEaK data, the broadcast address. And if you would search harder, if we have EF config output to compare, and some of the other bytes are the MAC address of the honeypot, so the sender address of the NoSEBrEaK packages. We also have candidates for port values, and again 1111 and 2222 are the ports we used in our example for sending out the data. And we have a list of possible values in this data block which could be IP addresses, and 10, 11, 12, 1 is the address of our honey wall, 10, 11, 12, 2 is the other address of our honey wall. We have, so we could narrow down the possible addresses of the honey wall from a 2 to the power of 32 about to a dozen. And the magic values too, which are 32-bit values to identify the NoSEBrEaK packages and to hide them, we have a good dozen of candidates which could be magic values, and in this case the magic value we had used was dead beef. It's also found. And the nice thing is this NoSEBrEaK also gives us the addresses of key functions in the NoSEBrEaK module, the init function and the cleanup function. So how could we disable NoSEBrEaK? There's a very nice way NoSEBrEaK has built-in disablement by the cleanup function. We just have to call it. And friendly like it is, it removes the hijacked syscall table pointer, fixes up everything, and we are happy ever each after. The memory of the module is not freed, but we don't really care. The little problem is that the cleanup function in NoSEBrEaK is implemented buggy, and that after the cleanup there are still fragments in the network stack from the NoSEBrEaK module, so you probably shouldn't run a production server with a disabled NoSEBrEaK module for days. But the machines keep up. They usually start crashing when you shut them down. The more obvious way would be to just overwrite this read pointer again in the system call table with the original value. The problem is how to get the original value. And the crazy way is to just leave this read pointer how it is and patch over the NoSEBrEaK module to get rid of the logging functions. That might be feasible if NoSEBrEaK is not as a module but compiled into the kernel, then probably it's your only resort to patch the kernel at this place.
So in the first part we saw how to detect NoSEBrEaK, in the second part we saw how to disable it, and now in the third part we want to take a look at how to avoid logging. Why do we have to do that? Because there's something that we can't stop to being logged. For example, all network traffic has to be logged because we are connected to a honeypot and we have to use that line. So everything that's flowing in and flowing out can be monitored. Also, NoSEBrEaK allows us to see everything what's read by the system. So all calls to read are also or can be logged. So we have to find a way to disable it. So, and if you compromise a honeypot and then sometime after that the operator will notice it and perhaps we will do some analysis. Perhaps we'll shut it down and do some forensic. And with the help of the forensic analysis, he'll also obtain some data that you left on the machine. Also, perhaps your servers will do some kind of logging to the syslog that can help the operator of the honeypot to see what's going on. So there are some ways we can't stop to something that we can't stop to be logged. But perhaps we can do something against that. Perhaps logging of network traffic. As I said before, if I encrypt my network traffic, the operator can log it, but it's useless for him because he can't decrypt it. So whenever possible, I should use encryption and not leave the keys on the machine. And the problem is, how do we deliver our first exploit? The first exploit is problematic because NoSEBrEaK is running on the box. So everything what's read by this exploit can also be monitored and can be used for analysis later. So we have to find a way to deliver our initial exploit in a secure manner, perhaps via an HTTPS exploit. As we saw in the first demonstration, we use a vulnerable HTTPS server. Another point to avoid logging of network traffic that's probably very hard is to disable the logging hosts. It's not always feasible because you can't be sure where something is logged and perhaps the logging server is far away or very secure. So perhaps this is left as an exercise for you. So use encryption whenever possible and then nothing can go wrong, basically. NoSEBrEaK hijacks read, so everything that's read is monitored. And who does use read? Nearly every program, because everything what's read, perhaps in a configuration file or any other file, has to pass this read, so everything is monitored. Can we perhaps avoid it? Yes, there are ways. For example, all network programs use receive. Receive has the nice property that it doesn't use read. So if you read from a socket via receive, nothing is logged via NoSEBrEaK. But can we, okay.
But one problem is, which was hard to grasp for us at first, if we have this encrypted communication with SSHD, where is the read happening that NoSEBrEaK still is able to intercept? We have the socket, which usually uses receive, but even if it would use read, there's the encryption around the communication, so nobody should be able to log anything meaningful except of perhaps timing information or something like that. But the thing is that the SSHD isn't able to do anything interesting. If somebody is logged in, the SSHD connects to a shell or something else. And this connection is where NoSEBrEaK attacks, because there's a file descriptor on every end at the shell and at the SSHD connected by a Unix pipe, and there the bash is reading the keystrokes you send via the SSHD, and the SSHD is reading back the answers. And that is where the logging takes place and where encryption doesn't help us so far.
So now we take a look at what is NoSEBrEaK logging. As you see on the right side, there's the NoSEBrEaK header. You see that there's a magic number that's used to to identify a valid CBEK packet. The version number is currently 2, and there are some other things like the timestamp, the PID, the UID, the file descriptor, the first 12 byte of the program name, and the length of the total packet. So if you take a look at this, PID and UID calling read are locked. So basically, this is an information the operator of a honeypot has. The file descriptor is the FD. Perhaps we can fiddle with it. Perhaps we can change 0, 1, and 2 so that they have another meaning, and so we can make the work of an post owning for the forensic much harder. On the other side, you can see that the name of the program or the first 12 byte are also locked. Perhaps we can even fiddle with this if we copy the binary to another location, or if we do other things, we can fiddle with it and make the work of the forensic much harder. So, as we saw, the tool DD helps us to squeeze many data through the line. We do effectively a kind of DOS, denial of service attack, against the honey wall. So this helps us because now all logging is not reliable anymore. If we just send enough data through our network interface, it's probably that some packets are lost. As we saw in one of the demos before, there were a message from NoSEBrEaK that it lost some packets, and so the logging of NoSEBrEaK is unreliable if many data are sent via the network. But that's not very reliable for us because we can't say what is exactly not logged. So it's not reliable for us. So we have to look for another way. Another way would be mmap. Perhaps we can use mmap to emulate read. And can we do it? Yes, we can. Exactly not everything, but we can most things that we can do with read, also mmap. Mmap has the nice property that it's very hard to intercept because, for example, if I just map 2 gigabytes of memory into another location, then I can't log everything. I can't log 2 gig of memory and send them via a network interface. mmap has the nice property that it works on all regular files. So everything what's a regular file can be mapped directly into memory, and then I can work with it. There are some nasty things if I want to do. If I want to use, for example, def random, I can't use any device. I can't use any pipe because pipe isn't a file, so I can't mmap it. So I've got some things I can do, not everything, but mmap is enough. I can do most things that I have to do.
So we are looking for a way to completely avoid read. The first thing is we have to say goodbye to our shell, because the shell uses read to get your keystrokes, as shown above. We need something which directly talks to the network and directly executes the commands. If you think back of the picture I've shown you, if the SSHD would execute the commands instead of the shell, there would be nothing to log for NoSEBrEaK. A very nice thing which helps us at this is that the exec system call doesn't use read internally. Sometimes libraries are read after a program is executed via read. Sometimes they are mmapped. I'm not really sure which happens when. And script languages like Python read their thing in, but the original exec system call results in no read system call. So NoSEBrEaK can't log which programs are executed as long as they don't read any data. Another thing is that the process name, we can mess with that very easily. We can start to renaming things, for example, VI to date or something like that, and that will start giving the forensic examiner a really hard time to make sense out of the NoSEBrEaK log files. So we can read files unnoticed by mmapping then. We can possibly execute programs unnoticed unless they don't read to my libraries. Since file names are not logged, the names of the files we're reading from, we can give the impression of reading certain files. For example, I create a file temp XXX, which looks, the contents looks like a etc password VD file, and read that via cat or what else, and the forensic examiner again has a hard time finding out what's being read there and what's being happening. We can give the impression that we're executing programs which we don't. For example, we can copy a harmless binary like cat to a name like a binary we aren't supposed to run, like Oracle server or whatever, and start this. And again, the forensic examiner will have a hard time with that. So how did we get all these things together? We wrote this tool, KBS, which does the direct execution with the encrypted network communication. It's made that, so avoiding using a shell or any external tools where we can go without them. KBS is certainly proof of concept code, and what we consider somewhat innovative is that it's written in Python. It's a network attack tool which is written in a very high level language and gives us some really nice things and possibilities to play with it. And the nice thing is it's very independent on the target platform, as long as there's a Python interpreter, which is usually there because all the Red Hat tools use Python. Our program can execute there without regard of the used libraries and the used binary format and so on. The KBS can do everything you can expect from a basic shell. In fact, we could give the KBS client a front end like a shell, but because we are programmers and not system administrators, we more liked to do function calls instead of typing commands. And it's highly dynamic. It's interesting to note that in the last week, in the newest FRAC, the GRUG published a tool which has very similar aim, executing without using the shell and pushing your code over the network, executing it in memory without ever writing it to disk. But it has a very different architecture because it's written in C and you have to jump to so many loops to make something highly dynamic in C. KBS uses TCP sockets for networking, but also could use standard in or standard out or something else. For example, if you have an exploit which still has an open socket or an open whatever, you could use that for communication with KBS. And on top of that socket, it implements a crypto layer based on Diffie-Hellman. Basically, we couldn't use any other form of encryption because we have to assume that the initial exploit code, so the KBS server, is captured by a forensic examiner. So there's no sense in putting keys into the binary. Oh, it's not really a binary because it's a Python program. But that's not that bad because Diffie-Hellman protects against passive attacks and the Honeywall is just a passive device. So if we use Diffie-Hellman, there isn't any way that the communication can be decrypted post-mortem. Only a man-in-the-middle attack could break our Diffie-Hellman. Together with this Diffie-Hellman, we use AES. And the crypto layer also provides compression and random length padding so that that from the network traffic, nobody can guess at the sizes of our commands and guess which commands we might have executed. The main problem for implementing the crypto layer was getting entropy, since we couldn't use sysread without being locked by NoSEBrEaK. We couldn't use def-random with nmap. We had to read from def-random, and we had to assume that the data from def-random is locked by NoSEBrEaK. And so, you know, if you have no random data, or if the attacker knows your random data, all your cryptography is already compromised. We countered that by doing something like the DD attack, and hoping that some of our input from def-random would be dropped by NoSEBrEaK, and we did some other things to get some entropy. For example, we used thread races, and we hashed the whole content of var and tmp, which is slow but should give us some kind of entropy. And we used the network counters and the program table and so on. So basically we stuffed everything in and hoped something would be at least enough to get random data with will get a forensic examiner a bad time. And on top of the crypto layer, there's a Python-specific key-based layer which use serialized objects to transfer commands and so on. And that is a nice thing. With using Python, I could transfer very complex data between the client and the server. The key-based layer is designed to be asynchronous, but at the moment it isn't implemented. And commands can work on several objects on the server at once. So I can several commands in one data package and can basically give the command several parameters like files to work on. Twist on Keybase is that the Keybase server just knows one command, add command. So I have to transfer the Keybase server to the target host to get my whole thing running, but somebody examining it can learn very little about it because it just knows this one command, add command. And then I connect via a cryptographic connection and push all the intelligence in the server. Basically, the code I really use in Keybase is taken from the client, serialized at an in-memory object, not at source code, and sent to the server, where it's added to the namespace and memory space of the server and now can use and be executed from the client. I found out that this is also a very nice thing to develop code because you never have to restart your server while development. You just edit the client and start the client and it pushes again the new code into the server and executes it there. This means that most of the intelligence and code in Keybase just exists in the RAM, at least as long as there is no swapping. Commands implemented in our proof of concept code is reading and writing from files using mmap, so no logging by NoSEBrEaK, secure deletion, so overwriting the file, then truncating it, then renaming it, and then deleting it. Direct execution via exec. It would be nice to add something which executes other programs without using the kernel, like the userland exec thing, but implementing that in Python will be really hard. And listing directories and so on. So more information and in-deep academic discussion of the subject can be found in our paper NoSEBrEaK Attacking Honeynets, which was published at the Information Assurance Workshop in West Point and won a Best Paper Award. And on my homepage, the URL is down there. There also are the slides available and movies of all the demonstrations. So if you think the demonstration here was too small, the font or something like that, you can replay them there. So, questions? No questions? Ah.
Just to point out, when you're talking about getting the IP addresses for NoSEBrEaK client, select server, the Honeywell doesn't actually have to have an IP address. It just pick up the packets so you can connect somewhere else through capacity.
Yeah, the question was, if it was a statement that the Honeywell doesn't have to have an IP address. That's right, but at least we can see what IP address the Honeynet operator put into NoSEBrEaK.
And you also have to provide an IP address for the logging host. So that doesn't have to be the real one, but you get some information. Right.
That's it. Okay, thank you very much.